third year in Seshadri's group. And yeah, so today I'm presenting on XPS, which is a surface technique that I've used a fair amount for helping to understand battery materials. It's a pretty, it's a really powerful technique that's used in a lot of different fields, like ranging from, yeah, I mean, it's not just limited to material science. It's a really powerful surface technique that can help you analyze surfaces in a multitude of different types of materials. I think even in the biomedical industry, they use it as well. Yeah, so I'm just gonna start. So feel free to just stop me whenever if you have questions, because we don't really have to wait till the end. I think this is a little more informal. So what is XPS? And well, maybe this doesn't totally apply to all the undergrads, but possibly to start thinking about that. How can it help your research or answer questions that you might have? And so XPS is traditionally thought of, I mean, it is surface sensitive technique. It's not limited to that, but it's a really powerful surface sensitive technique that's based on the photoelectric effect. So today, I'm also just going to give like a little bit about a brief theory about the photoelectric effect and why we can use it to probe the surface states. And so what happens on a really basic level for XPS is that light waves hit a surface of a material and then cause electrons to be ejected. And so I'll go into this in more detail later, but you basically measure the energy of these electrons and the number of them, and then that will give you information about the types of elements and the oxidation states of those elements. And there's a lot of advantages. So it's really surface sensitive. Like you can really go on just the top few nanometers. It has a really high detection limit, which also means that it's that you can even detect really, really small quantities of an element. So it's highly sensitive. You can get quantitative measurements. So it's not just a qualitative technique to say like, oh, we have iron and copper in there. You can also really quantify and get the exact percent of iron to copper, or something along those lines. You can get really valuable insight into the chemical bonding. So it can really tell you about the chemistry that's occurring in your system. So you're not only getting relative quantitative values between elements, but also how they're bonded. Some disadvantages: high vacuum isn't really a disadvantage, but it can be a slower technique, but it's also a more expensive technique. So yeah, that's the main disadvantage. But overall, it's a really streamlined technique to use that you pretty fast to get really good data. And
I
so
a quick chime in for the high vacuum. The high vacuum can be a disadvantage, especially if you need your system to remain at like a normal pressure. For example, if you have like, let's say if you wanted to look at the surface of your system with electrolyte there, you're not going to be able to do that kind of characterization here because you're in that high vacuum environment. So the high vacuum does add a lot of processing considerations with respect to sample prep, but yeah, so that is the
true. So I mean, you can't do liquids in a high vacuum, and you have to be very careful about if you're doing powders, which you can totally do. You have to really make sure they're adhered to some sort of tape to make sure that they don't get sucked into the vacuum. So yeah, it's just something to think about. But yeah, people definitely don't do liquids for XPS. So what type of information can you get? Well, you can you can understand the chemistry and measure the elemental composition of every single element except hydrogen and helium. So that's pretty powerful and gives you some advantages over other techniques like XRF, where you might not be able to get, let's say, like the lithium content or something. Yeah, once again, you can get the chemical and electronic state of each of these elements. after hydrogen and helium. And there's a lot of other techniques that I don't use as much for XPS, like doing line profiles. So for people that have, I don't know, let's say you have some sort of interesting pattern, or like you do lithography on a sample and you have really clearly defined regions of, like, let's say 2 different materials or MBE or something like this, then you can do a line profile across and see that change in the constituent elements. You can also do depth profiling. So they have this thing called the ion etching using a cluster gun. And with that, you basically bombard your sample with ions, and you can basically remove a small amount of that surface layer, take a measurement, and then use the ion gun again and keep going to get some sort of depth profiling for composition, which is useful in certain circumstances. And that ion gun you can also use just to clean your sample surface. So usually when you prepare any sample, you're just going to, it's called, I always forget, advantageous carbon. Rebecca, am I right?
It's like adventitious.
Adventitious carbon. And so
I don't, it just means atmospheric carbon. So I don't know why they don't call it that.
Which is, yeah. And so basically, if you're transferring your sample or something, because it's so surface sensitive, it can pick up things that maybe you don't want to measure or aren't actually part of your system. So you can use the ion gun to help clean that off and then get a cleaner measurement. And people use this in polymer to look at polymers, a lot of types of inorganic materials. Definitely, it's a big technique for thin film coatings. People use it for catalytic activity, looking at corrosion, adhesion, and also in some industries, definitely is used for failure analysis. Yeah. And so what is the photoelectric effect? In classical electromagnetic theory, the photoelectric effect was based on the hypothesis that light traveled purely as a wave. And so they believed that the energy of the wave was related to the wave's amplitude. And that would mean that the kinetic energy of the emitted photoelectrons should increase with light amplitude. So in this case, the beach balls represent the electrons. And so what in the classic theory, if you had a high amplitude wave, then you would eject your electrons with high kinetic energy. And if you had a low amplitude wave, you'd eject them with low kinetic energy. And then they also, in this theory, the rate of the electron emission, so how many beach balls are getting kicked off, should increase as the light frequency is increased. But this is actually not observed. So the classic electromagnetic theory was wrong in this regard, because the kinetic energy of the photoelectrons increases with the light frequency, not the amplitude. And the electric current actually remains constant as the light frequency increases. Yeah, and so what was observed was the electric current increases with light amplitude. So here where we have the high amplitude and we're saying, oh, we get high kinetic energy, that's wrong. If you have a high amplitude, then you get more beach balls kicked off, but not with higher kinetic energy. So we needed a new model to explain these results. And Albert Einstein won the Nobel Prize in Physics in 1921 for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. So in 1905, he proposed a theory of the photoelectric effect that light sometimes behaves as particles of electromagnetic energy called photons, where the energy of the photon in joules is equal to the Planck constant times the frequency of light. And so with this theory of the photoelectric effect, what would happen is if you V naught would just be some critical frequency of light. And so if you hit a surface with an amplitude that is less than the critical amount, you will not eject any electrons from the surface. If you hit a surface with a frequency of light that's greater than this critical amount, then you will eject electrons from the surface. And if you keep the same amplitude, okay, but then increase the frequency, so you can see the height of the green and the blue are the same, but there's a much higher frequency of the blue waves than the green, then you'll eject the same number of electrons, but with higher kinetic energy. And so the observation showed really good agreement with the model. So if we look at this plot, the electron kinetic energy versus light frequency, where V naught again is some critical frequency, if the incident light is less than this frequency, then you don't get any electrons ejected. So you see there, like, yeah. But the kinetic energy of the photoelectrons are proportional to the light frequency. So once you hit that critical frequency, then you'll start ejecting electrons. And this is a linear relationship. If the light amplitude is kept constant as the light, sorry, that I meant not to look on this right one. So yeah, this is all for frequency greater than the critical frequency. And it's a constant relationship between the light frequency and the current. But when the light amplitude is kept constant as the light frequency is increased, the number of photons being absorbed by the metal remains constant, so constant current. So it's just to summarize this photoelectric effect, the kinetic energy is equal to HV minus W, where once again, H is Planck's constant, V is the light frequency, and W is the minimum energy required to move an electron from the surface of the material. So when you have this minimum energy equaling Planck's constant times the critical light frequency, that is so you plug that in. For this effect to occur, the frequency of light has to be greater than the critical frequency. And so that's called the threshold frequency, and then you'll get the occurrence of the photoelectric effect. So just to summarize, electrons are bound in atoms, molecules, and solids, and they each occupy distinct states of well-defined binding energies. And when light quanta deliver more than this amount of energy to an individual electron, the electron can be emitted into free space with excess kinetic energy that's HV higher than the electron's binding energy. And this distribution of kinetic energies reflects the distribution of binding energies in the system. And so the reason I went into the photoelectric effect is because this is basically what the entire XPS, X-ray photoelectron spectroscopy is based off of, the photoelectric effect. And that's why it's such an important piece of theory to understand when you're using XPS. So how does this apply to the actual experiment that you're doing? What are you actually what are you actually measuring, and what variables are you actually getting out in an experiment? So this is the simple equation that describes what you're doing in the experiment. We have the E binding, so the binding energy of the electron is equal to the energy of the photon, so the energy of the X-ray photons being used, minus the kinetic energy of the electron, plus a work function. So this work function is sort of complicated, but can just be thought of as like an instrument correction factor. It's constant. It's sort of built into the software of the instrument anyway, so you don't really have to worry about that. And what you do know for sure is that from your source, for your X-ray source, you are always emitting a particular wavelength. So in our case, we're doing aluminum K alpha X-rays that have a fixed energy. And so this E photon is then fixed from the instrument, and the work function term is fixed. And so you measure the emitted electrons' kinetic energies, and yeah, so once you measure the kinetic energies, that's how you can then calculate the binding energy. And this is the information that's very particular to each element and the different oxidation states of each element. So at UCSB, we have a Thermo Fisher Scientific Escalab 2. I think this is the same instrument, the 250XI, something like that. It's really fancy, new XPS. And it's highly sensitive and has high resolution, very friendly user-friendly interface. And there's a lot of cool sample stages, actually a lot that I wish I could use just because they're really cool, but you can heat samples, you can, I think, apply voltage biases, you can just have a plain stage like this. This is the one we usually use for just measuring simple like powders or crystals or something. But yeah, there's a variety of stages you can use. And the primary components are this ion gun, you have a microscope and camera, the analysis chamber, so the entry chamber, the sample manipulator, and the X-ray source. And so what happens is this is the entry chamber. So you basically mount your sample onto one of the desired stage. You open this entry chamber door and you put in, so at the end of the sample manipulator rod, there's a little clasp that you can put your sample stage. So you open the door, attach your sample stage to the manipulator, close it, and then you pump down to a really high vacuum. Once it's high enough vacuum, there's a door between the entry chamber and the analysis chamber. And so then you open the door, you move your sample into the final analysis chamber, you drop it off in the middle of that chamber, close the door, and then pump to even higher vacuum. And then at that point, that's when you can sort of start your experiment. And that's when you, I'll show in the next slide a video of what's actually happening. But basically the ion gun shoots X-rays down. Your sample will emit some amount of photoelectrons, and they'll go up through this analyzer, which I'm not going to get into, but it's curved, and they use a magnetic field to sort of corral the electrons and then measure their energy and the amount of them. So what happens is you have the electrons emitted, then they're monochromated, and then they hit your sample, and then they're focused, their energy selected through that analyzer, and then detected. And so the photoelectron spectrum is then recorded by counting the ejected electrons over a range of kinetic energies. And so peaks will appear in the spectrum from atoms emitting electrons of a particular characteristic energy. And so on the periodic table, each of those elements has its own characteristic energy. And so even if you had a sample where you have no idea what the constituent elements are, by just doing an XPS measurement, you are going to get a pretty good idea of what those elements actually are by just knowing the binding energy of each of all of the electrons that you're measuring that are coming out of your system.
I wanted to mention a few things here. The reason why in these measurements in general we need a really high vacuum here is because if you didn't have a really high vacuum in these circumstances, your electrons that you have scattered off of your sample are going to collide with all of the different atoms that exist within the atmosphere in that chamber. And then you are going to basically get really fuzzy results because there's going to be different collision processes that occur there that are going to change the energies of the emitted electrons. And then you basically have no idea now really what your system really is.
I mean,
The
it's
other
not
thing-
even just the energies, it's also like the number of electrons. And this is the same principle why in FCM or TEM, you also need high vacuum environments.
Exactly. And then I also wanted to ask, with respect to the work function that you mentioned earlier, does the work function really just kind of take into account the sort of different aspects with respect to like the slowing of the electrons and the curving and sort of energy changes that might occur during that process?
Yeah, probably. I'm not exactly sure what Thermo Fisher is putting into their software for the exact work function, but I'm sure it's really worked out as well from standards.
Yeah.
Like it might be like backtracked through putting in like a really high grade sample of like silicon or something like that, and backtracking what the work function of the instrument is by looking at a couple of really high quality samples. That's what I would guess how they would backtrack out that work function, but I'm not sure.
Sense.
Yeah.
Oh, one more point. For anybody who doesn't know what the word monochromation means, really all it means is that it just makes it so everything is one same wavelength. We like,
So
yep,
it's
exactly.
exactly like
Exactly. Yep. Like Kira explained, basically, if you don't have one single incident photon energy, then then your spectrum doesn't mean anything, because all of the different energies are possible from the different constituent elements, basically.
if
But
this isn't fixed, then you're gonna have like, you know, whatever error you have in the energy of the photon is going to carry through to your binding energy.
Mhm.
So you can think of it that way. The more accurate, the more monochromated it is, then the more accurate the binding energy. And as I'll show in just a small example, it's really important that you have a very precise binding energy, because that can be really important for ants, like especially if you're looking at just oxidation states within one element. You need really high confidence in your binding energy to have confidence in your results.
Yep. Thank you.
Yeah. Oops. And there's a lot of different types of samples you can measure. As I said, there's like a ton of really cool stages that aren't commonly used, but these are so usually I use like some sort of standard stage where we're just putting a powder crystal on, but there's so much flexibility. You can use any geometry of like any geometry crystal or shape, any powder, and the only thing that you have to make sure you do is that to make sure that the sample is very well adhered to the stage so it doesn't get sucked off into the vacuum. And there's also this really neat air-free holder that Tom Mates, the person that runs the XPS, designed, which can keep everything air-free if necessary, which is useful in my field, which is batteries, because you can make some sort of ex situ sample and open it in the glove box and then put your powder onto this air-free stage and then take it into the XPS so that you never expose the ex situ sample to air, which could change the chemical properties of your sample potentially. And so yeah, this is just like an example of some powder I measured air-free and a crystal rod that I measured as well. So it's really flexible. The last thing I want to talk about is just a really short case study as an example to show a couple of questions that you can answer. So I'm showing the crystal structure of tungsten vanadium oxide, which is a fast charging Wadsley-Roth phase. And this is an interesting block material. 3x3 blocks are tiled, and they have mixed occupancy of tungsten and vanadium. So when you synthesize it in this ratio, in 0.2 to 0.8 ratio. But we don't know for sure. I mean, we want to confirm because you can't tell with X-rays really exactly what that ratio is. So on the right, I'm just showing a discharge curve of the material that shows that it can charge really fast. 10C is 6 minutes. So storing over 100 milliamp hours per hour in 6 minutes. And so we want to ask, is the tungsten vanadium ratio in this material really 4? And then as we insert lithium into the structure, so we're discharging down, we're going from 0 to 4, how are the oxidation states of the tungsten and vanadium changing? So usually the first thing you measure when you measure a sample in XPS is to do a survey scan. And this is generally, I would say, like sort of an eagle's eye view to get an idea of what constituent elements are in your material. And you can also quantitatively get the ratio between elements. What this won't tell you, it's not high enough resolution to get the chemical energy, or sorry, to get the to get precise understanding of the chemical bonding environment. So that's why we have to do high resolution scans to understand more of the chemistry that's going on. But just from an eagle's eye view, we do this survey scan, and each peak here represents when that detector is measuring a certain number of ejected photoelectrons at this energy, right? So peak here, peak there, and that's just when that detector is getting hit with the photoelectrons. And the table shows the different elements that we found in the sample that are exact binding energy. So here you can see the tungsten 4F is at 36 electron volts. So that one's right here. And then you can get the atomic percent. And so our expected vanadium to tungsten ratio was 2.4 to 0.64. And using the XPS quantification, we get 3.93. So we can conclude that we did in fact synthesize the sample with the amount of tungsten and vanadium that we were expecting.
Kira, can you detect oxygen with XPS?
Yes. Yeah.
Why don't you detect any oxygen from this?
I didn't include it in the, so
Okay.
sometimes if you're, in this case, for getting the atomic percent, it's the way I'm getting the ratio is I'm not doing all of them holistically. I'm just taking the atomic percent of the vanadium and comparing it to the atomic percent of the tungsten, because this is generally will give you a more accurate result. Just comparing the two transition metals to each other instead of also including oxygen in that mix. And that's also a common way that people look at like quantify elements in XRF too. If you're looking at an oxide, usually you'll also compare the transition metal ratio instead of also including oxygen.
Okay. So is the oxygen peak there just not taken into account?
Yeah, I didn't label it on this spectra.
Okay, cool. Thank you.
Is it the one next to vanadium?
Yeah.
Okay.
Yeah, so the oxygen is right here.
Okay, cool.
Yeah,
Thank
the vanadium and oxygen can sometimes be convoluted. So that's one of those elements that you have to fit both when you fit the spectra.
Okay.
There's this really old but super useful handbook of X-ray photoelectron spectroscopy that is a really good fast starting point. Basically, each page is a different element, and you can just get an idea of what the different binding energies would look like for, let's say, vanadium in different environments. So vanadium nitride, vanadium metal alone, vanadium oxide, etc. And so you can just quickly, at first, I usually refer to this handbook for determining what binding energy region to scan. So at first, we do the survey scan where we're doing the whole binding energy region that you can measure with the XPS. But to get higher resolution information, let's say about vanadium, you have to do a much smaller subset. So instead, we would really focus on this region right here to get much more accurate information about the shape of the, to get the more information about the exact shape of the peaks so that we can fit them better to understand the chemical bonding. And so you can just look here to see like, okay, what binding energy region should I focus on? And this is an example then of going more high resolution and getting the vanadium 2p binding energy. And these are high resolution scans that were performed on those non-air exposed samples. So that special sample holder that I showed before. And we're trying to understand, we're starting out with 0 lithium and we're inserting 4. What does how does the chemical environment and the oxidation state of vanadium change as you insert lithium? And so online you can find, there's lots of information, but depending on the element and like which orbital you're looking at, there's really locked ratios for the peak width and intensity. And so you have to make sure you adhere to those rules for how to analyze the data. And it's possible to fit the spectra to get a quantitative ratio of the oxidation states. So this is the high resolution scan, and I'm able to fit it with 2 different peaks. So these correspond to vanadium 5+ and 4+. So as we insert lithium, we start out with a combination of vanadium 5 and vanadium 4+. As we insert lithium up until around x is equal to 2.2, we see that slowly we're getting a higher proportion of vanadium 4+, up until max lithiation at 3.9, where we see the emergence of vanadium 3+. So we're getting a combination of all 3 oxidation states. And then when we charge the material, so when we pull out all that lithium again, we return to a majority 5+, vanadium 5+ state with some 4+, sort of similar to what we got in the pristine material. Yeah, and then that's it.
Thank you, Kira. Does anybody have any questions?
Actually, let me just say this one last thing, which is sort of interesting. You might ask here, okay, but why are there 2 peaks? What do those mean? And it's called the XPS electronic effect splitting. And so depending on what orbital you're in, you're going to get a singlet or a doublet. So all orbitals except the s orbital give rise to a doublet. And those 2 states have different binding energies. And so, for example, when I was showing the vanadium 2p, that will be a doublet. So we do see 2 peaks, and they'll have like a fixed area ratio that they'll be in. So in this case, you can see that it's like a sort of like a 1:2 ratio, which you can sort of even eyeball it, that it is following that rule. And so this is due to spin orbit coupling, and you just have to pay attention to that. But yeah, okay, cool. That was it.
Wonderful. Thank you. Thank you, Kira. Anybody have any questions that they want to ask? No questions at all?
No, I'm giving a presentation. No, that's okay.
Okay. All right. Well, thank you so much, Kira, for giving that presentation.